this is the last section of the semester. Okay, electrochemistry. This is actually what I study in graduate school.
Looks like raspberries.
Raspberries?
Yeah.
Okay. So why are we studying this? Because it's in the course outline. Okay, that's why we're sticking this in here. The author of the book didn't read our course outline, so we just got this one section from chapter 18. So this is about balancing redox equations, balancing redox reductions. Oh my goodness, balancing redox reactions. There we go, got the right words. So we've talked about oxidation and reduction. We've looked at oxidation and reduction reactions. And so we're just going to look a little more at balancing the reactions. So first we need to review a little bit, because I'm pretty sure many of you have just kind of relegated this to the back part of your brain. So we had a mnemonic to help us remember things. It was oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And so that serves us well in some situations, but sometimes it's not real obvious what's losing or gaining electrons. And so we also need to remember that oxidation is an increase in the oxidation state, and that reduction is a decrease or a reduction in the oxidation state. So if we look at this example where we have calcium metal reacting with liquid water, we're forming calcium hydroxide and hydrogen gas. And so, it's not immediately obvious what's going on with electrons, but we can look at oxidation states and identify what's being oxidized and reduced. When we're balancing these, mass has to balance, but we also need to have the charge balance. And so the way we do this is we take the equation and we break it into two half reactions. They're each part of the reaction. So two half reactions. We balance them individually and then we put them back together. So what we'll do is we'll take the oxidation part. So this calcium had an oxidation state of 0. It went to +2. And so we'll take the calcium and the calcium hydroxide and we'll work with that as one half reaction, the oxidation reaction. And then here, this hydrogen is going from +1 to 0. It's being reduced. And so that will be the reduction half reaction. Let's review oxidation states. The rules go in order of priority. So if you have conflicting rules, the first rule wins. So free elements always have oxidation states of 0. Monatomic ions have an oxidation state that's equal to their ionic charge. So oxidation state and ionic charge are sometimes the same number, but be very clear that they are not the same concept, okay? The sum of the oxidation states of all the atoms in a compound is 0. So if we've got sodium chloride, we know that the oxidation states for these two ions have to add up to 0. If we have a polyatomic ion, then the sum of the charges has to equal the charge on the ion. So in nitrate ion, overall it has a -1 charge. The sum of the oxidation states for everything in it have to add up to -1. If you have a neutral molecule, the oxidation states add up to 0. In their compounds, metals are always going to have positive oxidation states, just like they always form positive ions. And the group 1 always have an oxidation state of +1 in a compound. Group 2 is always +2. And then we have the nonmetals, and that's where it's a little, requires a little more understanding, a little more remembering. And so we follow this table. The nonmetals, I think of them as wanting to have an oxidation state that is equal to their ionic charge as a monatomic ion. So fluorine as an ion would be fluoride, would have a -1 charge. So fluorine would like to have a -1 oxidation state. Hydrogen as an ion is usually +1. Oxygen is usually -2. And then group 7A, -1, group 6A, -2, group 5A, -3. Why do they like those particular ionic charges. Do you remember? Full valence shells, right? They become isoelectronic with the nearest noble gas. It's more stable energy-wise. So remembering the oxidation state shouldn't be a problem. It's the same as the charge that it would take as an ion. What's hard to remember is the order. And so that's where we talked about noodles. Pho is noodles, right? What ethnicity is that? Vietnamese or?
Yeah.
Vietnamese. So Vietnamese noodles, really yummy, right? It's spelled P-H-O, pronounced pho. So we're going to misspell it a little bit, but F-H-O. So fluorine, hydrogen, oxygen, and then they go in reverse group order, 7, 6, 5. Okay? So when you've got several nonmetals and you're trying to pick who gets what they want, this is the order. Okay, so this is the procedure for the half reaction method of balancing aqueous redox equations in acidic solution. And then we're going to do in basic solution. Very, very similar. The first thing we do is we have to assign oxidation states to all of the atoms. And then we'd like to identify what's being oxidized and what's being reduced. Then we separate them into two half reactions, one for the oxidation and one for the reduction. Then you balance each half reaction. First, according to mass, balance everything besides hydrogen and oxygen, then balance the oxygen, and you do that by adding water to whichever side you need. It's okay. It seems like, oh, we're just throwing stuff into this reaction. But it's an aqueous reaction. There's lots of water molecules in there. It's okay to just put some of them into the equation. And then we balance the hydrogen by adding hydrogen ions. This is acidic solution. There's going to be hydrogen ions around. Then we have to balance with respect to charge. So you look at the overall charge of the reactants and the overall charge of the products. You're not trying to get them to zero, you're just trying to make them equal to each other. And you balance the charge by adding electrons. And you'll find that one of the half reactions needs electrons on the reactant side and one needs them on the product side. After you've done that, then you make the number of electrons in both of the half reactions equal. And we'll do some examples, and hopefully this will all make a little more sense then. After you've got the number of electrons equal, then you add the two half reactions together. You're going to cancel out the electrons and other things that cancel out, and then you should always double check that it's balanced at the end, both with respect to mass and to charge. So let's do a couple of examples. Here I've got the summary of the instructions over here. So let's balance this redox reaction. Well, first we have to assign oxidation states. What's the oxidation state for solid aluminum? 0. This is an element, doesn't have a charge, so 0. How about copper 2+ ion? So this has an oxidation state of +2. How about Al 3+, +3? And copper metal? 0. Okay, so if we look at the aluminum, it's going from 0 to 3. It's being oxidized. And the copper is going from +2 to 0. It's being reduced. So I'm going to separate these into two half reactions. I just like to do them in the same order that they were presented. So we've got aluminum solid going to Al3+, aqueous. And then we have Cu2+, aqueous, going to copper solid. So we balance with respect to mass. Here I have one aluminum and one aluminum. It's already balanced, right? There's no hydrogens or oxygens to mess around with. We're starting with a simple one. Here, one copper and one copper. Mass is balanced. Then we fix the charges. In this first reaction, we have a total of 0 charge on the left and +3 on the right. The way we balance it is by putting electrons either on the reactant or the product side, and we're trying to make the sides equal in terms of charge. Well, if I'm adding negative charges, I should add them over here, right? If I put 3 electrons over here, 3 electrons, 3 negative charges, and 3 positive charges gives me a total of 0, right? So now I have 0 charge on each side. And then for the copper, I've got +2 here and 0. So I'm going to want to put 2 electrons over there. So 2 negatives and 2 positives, I get 0 over here and 0 over there. Still with me? Now, when I put these two back together, I don't want electrons showing up in my equation. When aluminum becomes aluminum ion, it gives up 3 electrons. When a copper ion becomes copper metal, it takes 2 electrons. But there would be 1 electron just left over, and we can't have leftover electrons. So what we're going to do is we're going to find the least common multiple of 2 and 3, which is 6. So I need to take this top equation and multiply by 2. So if I multiply that equation by 2, I'm going to get 2 aluminums, making 2 aluminum ions, and I'm going to have 6 electrons. Okay? It's still balanced by mass and charge. And then what do I want to multiply the bottom one by? 3. So I'm going to get 6 here, and 3, and 3. So I've got the electrons equal. 6 on one side, 6 on the other. Now I can add this together. There are 6 electrons that are released by this half reaction and 6 electrons that are taken up by this half reaction. So you think of them as canceling out, right? They don't show up in the final reaction. And then I'm going to copy down the other stuff. So I've got 2 aluminums and 3 copper ions. And 2 aluminum ions, and 3 copper atoms. And then you should check that it's balanced by mass and charge. Now on the left I have 3 times 2 plus 6 charge, and on the right I have plus 6 charge. In this equation up here, it was balanced with respect to mass, but the charge wasn't balanced. I had +2 on one side and +3 on the other side, and that's not balanced. You can't have a chemical reaction and just have charge appearing or disappearing. Any questions?
Why is it a +6 charge?
Because I have 2 aluminum atoms, and they are each 3+.
Okay. Okay.
Any other questions? I'm going to skip this one and go to one that's a little more fun. I did this one yesterday. So if you want to see that, you can go to the YouTube video. And I did this one yesterday, and I did not do this one. So we're going to do this one. So here we have a copper and nitrate ion, and we're making a copper ion and nitrogen dioxide. What's the first thing we need to do?
Check masks.
Oxidation numbers, oxidation states. So the oxidation state for copper is 0. And then we've got nitrate ion. This is an ion, and so we know that the oxidation states of these atoms within it have to add up to -1. We've got 2 nonmetals, we've got nitrogen and oxygen. Who gets their preference? Oxygen. Because we've got F, right? FHO, O gets preference. So O wants to be what?
-6. Or -2.
-2. Each of them is -2, but there's 3 of them. So that's a total of -6. And then the nitrogen Don't know what it is. And this has to add up to -1. So what's the x?
5.
It's +5. There's different ways to think that out. So we got +5 and -2, and then over here a copper ion is what?
2 plus.
Yeah,
Plus 2.
it actually says right there, 2+. So this is a +2 oxidation state, and we got NO2. Again, with the nitrogen and the oxygen gets its preference, and so oxygen still wants to be -2. But now there's 2 oxygens and 1 nitrogen, and this is a neutral molecule. And so these are going to add up to 0. So we've got 2 times -2. It's adding up to 0, and X is the nitrogen. So what does it have to be?
You mean multiplied?
Multiplied?
2 times -2?
We've got 2 times the -2, and that combined with the charge or the oxidation state of nitrogen have to add up to 0. So this would be X minus 4 equals 0, so X equals 4. So the nitrogen here is +4. So we should be able to look at this and say, well, what's being reduced? Which thing has its oxidation state going from a higher number to a lower number?
Nitrogen.
Nitrogen. And what's being oxidized?
Copper.
The copper. It's going from 0 to +2. So I'm going to follow, didn't mean to do that. I'm going to follow copper, and they're going to be together in 1/2 reaction. And the nitrogen is going to be in the other half reaction. And so I've got the copper going to copper ion. And then I've got the nitrate ion going to NO2 gas. Okay? What's the next step?
Masses.
Mass balancing. Do I need to do anything to the top reaction? No, it's already balanced. But this one is not balanced. I've got 1 nitrogen on each side, but I have 2 oxygens here and 3 oxygens there. The nitrogens are balanced. So I don't want to just stick coefficients in here because you're never going to get it to balance, right? I need 1 more oxygen on this side, don't I? I'm going to balance the oxygen by adding a water molecule. So H2O, and that's going to be a liquid.
Why aren't we doing the like the +2 E minus on the copper? Like we did
We're
for the-
not balancing the electrons yet. We're taking care of the mass first.
Oh,
So now I've got 3 oxygens on this side of the arrow and 3 oxygens on that side, but now I threw hydrogens in there, and so I have to take care of those. We balance the hydrogens by adding a hydrogen ion. So H+, that's going to be aqueous. I need 2 of them, right? 2 H's and 2 H's. So now we've got mass balance on both. Now we balance the charge with electrons. So what do I need to do to the copper half reaction? Yeah, we need to put 2 electrons on the product side. This side is 0 in charge, and by adding 2 electrons, I can make this side also 0. Now down here, the things on the right don't have any charges, so those add up to 0. And over here, I've got 2 +1s and a -1. So that adds up to a +1 overall charge. So if I put 1 electron here, then the charge on the left side will be equal to the charge on the right side. Okay? What's the next step? Yeah, we have to multiply the bottom one by 2. We need to make the number of electrons equal so they cancel out and don't show up in our final balanced equation. So I've got 2 electrons here. I want there to be 2 electrons here. To do that without messing up the balancing, I have to multiply everything by 2. So it would be 2 electrons, and 2 times 2 becomes 4 hydrogen ions, and a 2 here, and a 2 there, and a 2 there. Still balanced. Everybody okay? Next, I'm going to combine these equations. The electrons should always cancel out because we're setting it up that way. So the electrons went away, and now I'm just going to copy the rest of the things down. The exact order that you copy them down in doesn't really matter. And even mastering chemistry is okay with you just putting them in any order, because 1 plus 2 is 3, and 2 plus 1 is also 3, right? It doesn't matter what order you put them in. I like to just follow the same order that's up there. I don't know why. Just figure, well, they wrote it that way. Maybe it's a good way to write it. But again, it doesn't really matter. So the copper, from the top reaction, there's only one. And then I'm going to do the nitrate. There's 2 nitrates, aqueous. And then I've taken care of this one and this one. I also have 4 hydrogen ions. So I need to put those in here. And then I'm going to go over to this side, and I'm going to look for the copper ion. There was one of those. And the nitrogen dioxides, now there's 2 of those. And 2 water molecules. And that's our balanced chemical equation. Any questions? There's a lot of steps, yeah. And that's why we're doing several examples, and the directions are in your textbook. Just follow the directions. So there's lots of directions, but each of the steps is not that hard, right? It's just remembering what to do next. Well, that was acidic solution. But what if this is going on in a basic solution? A basic solution has extra hydroxide ions in it. And so the way we would balance this is we would balance it as if it was an acidic solution. So all the steps that we've just done, when we get to the end, though, we're going to add hydroxide ions equal in number to the number of hydrogen ions that show up. And we're going to add those to both sides of the equation. I did not do that one yesterday. I did this one in lecture yesterday, so that one's in the YouTube video for yesterday. So we're going to do this one. So balance the redox reaction in basic solution. So I'm going to say, oh, basic solution. Okay, I'm going to set that in the back, and I'm going to do acidic solution, and I'm going to fix it. So what's the first thing we have to do? Assign oxidation states. What's the oxidation state of I minus? -1. And sometimes it's nice to just skip something that looks icky and go do the others first. What about I2? 0. There's 2 iodine atoms covalently bonded together. Their oxidation states have to add up to 0 because it's a neutral molecule. And so they're both going to be 0. And then I like the looks of this one better. So manganese dioxide, this is that brown junk that stained our glassware when we did the lab practical. So we've got manganese and we've got oxygen. So monatomic metal ions have an oxidation state equal to their charge. But this is not group 1A or group 2A. This is one of those transition metals where they could be all kinds of things. So it's easier to just look at the nonmetal first, and the manganese is going to be whatever it needs to be so the charges add up correctly. So what does oxygen want to be? -2. There's 2 oxygens, so we have a total of -4 charge. This has to add up to 0. If X is the manganese has to be +4. So let's go back to this one. So here we have permanganate ion. It has a minus charge. Again, the oxygen is going to get to be what it wants to be. It gets its choice. It wants -2. There's 4 of them, so we have a total of -8 from the oxygens. And this time it has to add up to -1. So what's X? 7. So I've got iodine. Is that being oxidized or reduced?
Which ones?
Oxidized, iodine. The iodide is going from -1 to 0. That's an increase in oxidation state. There might be questions on the exam that ask you to identify what's being oxidized and what's being reduced. So what's being reduced here?
Permanganate.
Not the permanganate itself, the manganese in the permanganate. The oxygen isn't changing. So it's the manganese
And that's being reduced.
reduced. There always has to be oxidation and reduction together. You can't have just one. So I'm going to write these separately. I've got the I minus, aqueous, and that's becoming I2, aqueous. And then I've got the permanganate ion, aqueous, and that's going to MnO2, aqueous. So my two half reaction. What do I balance first? Mass or charge? Mass. So here I have I minus and I2. How can I balance the mass there? I need 2 iodides. That's why you don't want to balance the charge first, because when you balance the mass, it might mess up the charges. So let's look at this one. Always leave oxygen and hydrogen for last. So we're going to check the manganese first. 1 manganese, 1 manganese. Okay. I've got 4 oxygens and 2 oxygens. I can't just multiply one of them by 2 because that'll change the manganese. The only way you can do this is by putting water in. So I've got 2 oxygens on this side, 4 on that side. So I'm going to put 2 water molecules on this side to balance my oxygens. And then I have to take care of the hydrogens that I just introduced. So I've got 4 hydrogens over there, so I'm going to add 4 hydrogen ions over here. The reason we don't balance this straight out with hydroxide ion is that the hydroxide ion has hydrogen and oxygen in it, and it makes everything very, very complicated. So we're just going to stick with the hydrogen ion. We're going to pretend it's acidic solution until the end, okay? So we have mass balance, we need charge balance. Here I have a -2 charge over here and a 0. So I'm going to add 2 electrons on the right side. Balance the charge. Down here, I've got no charge on the right, and I've got +4 and -1, +3 charge over here. So if I put 3 electrons in there, that'll bring that down to 0. Any questions? Mm-hmm.
How do you choose between water and hydrogen on either side?
You use water to balance the oxygen. You balance the oxygen first using water, and that'll bring hydrogens in, and then you take care of the hydrogens with hydrogen ion. Now we need to get these numbers of electrons the same. So we need to multiply. We're going to go for 6. So I multiply this bottom equation by 2 to get 6, and 4 times 2 is 8, and that's going to have a 2 and a 2, and this will be 4. I just multiplied all the coefficients by 2. The top equation I need to multiply by 3 to get 6 electrons. And so I'm going to have 3, and this will be 6. Okay? Now, you can go in and take care of the hydrogen ions with hydroxides here. I'm going to leave it for the end. The problem I worked yesterday, I took care of it now. This will give you 2 different ways to look at it. Yes?
Why did you multiply by 2 throughout the whole thing?
I multiplied all of these by 2 because I want the same number of electrons in the bottom equation and the top equation so that they'll cancel out when I add them together. Because before, if I just added these two without the blue numbers, I'd have one extra electron over here, and I don't want any electrons showing up in my equation, because you can't have just free electrons floating around in solution. So let's add these together. The electrons cancel out, and I've got 6 iodide and 2 permanganate ion and 8 hydrogen ions. And that takes care of everybody on that side. And then I've got 3 I2, and I have 2 MnO2, and I'm running out of space. I'm going to drop the state symbols. This would be the correct answer if it was in acidic solution. But it says right here it's in basic solution. So what we do is we look at how many hydrogen ions are showing up in this equation. We have 8 hydrogen ions. So what we're going to do is we're going to add 8 hydroxide ions to both sides. This is all beautifully balanced by mass and charge. We want to keep it balanced. But if we put the same thing on both sides, it's still balanced, right? I'm going to get rid of this scribbling and work up because I ran out of space. So I'm going to add 8 hydroxides on that side and 8, it's not an 8 hydroxides on this side. When I do that, it is still balanced, right? Well, what happens if we combine hydroxide and hydrogen ion? It makes water. So these two guys here, 8 hydroxides and 8 hydrogens, that's going to make 8 water molecules. You okay with that? And then I've got this 8 hydroxides over here. I have 4 water molecules on this side and 8 on that side. If I took 4 off of both sides, it would still be balanced, wouldn't it? So I'm going to take this guy out, and I'm going to make this a 4. I just removed 4 water molecules from both sides of the equation. It's still balanced, as long as you do the same thing to both sides.
Will we keep the hydroxide?
Yeah, this hydroxide then stays. These two, we combine them to make water. So now I've made a mess, and I'm going to copy it down neatly, or attempt to do so. So 6 iodide ions and 2 permanganate ions. And I've got 4 water molecules. And then on this side, I've got 3 iodine molecules and 2 manganese dioxide molecules and the 8 hydroxide ions.
Does that mean oxygen's out of balance?
Well, let's check. So oxygens, I've got 2 times 4, 8, and 4. So 12 on this side, right? And then over here I've got 2 times 2 is 4, and 8 is 12.
I missed the 2 in front of the marinate.
That's okay.
So you add as many hydroxides as you have.
Hydrogen ions. You look at your hydrogen ions, and however many of those you have, you add the same number of hydroxides. The reason behind that is that will neutralize all the hydrogen ions. It turns them into water molecules and gets them out of the equation. And it's much easier than trying to balance it in the first place with hydroxide. Question?
And for acidic solutions, we keep
Yeah, for acidic solutions, you would ignore the green here. Just the blue, that would be balanced in acidic solution. Okay? Now, can you actually have a solution of just iodide ions without any cation? No. It would have to be like potassium iodide or ammonium iodide or something, right? And you can't have just permanganate ions either. It's got to be like potassium permanganate, right? And when we get down to our balanced equation here, I've got hydroxides over here, and they need a cation too. So what you might see, in fact, you will see on the exam, is an equation to balance where it doesn't just say I minus. It'll say maybe Ki, and it won't have the charge. And then there'll be KMnO4. So what you do is you recognize this is just a spectator ion. It's not showing up over here. And it's hard to imagine how it would show up over here, right? Because there's no anions for it to be with. But when we do this equation, we see that, yeah, there are hydroxide ions for it to be with.
So when we do that, would we say that the potassium iodide is the charge would be 0 in that initial part?
Well, the potassium would have a +1 and the iodide would have a -1. It doesn't actually change the oxidation state of the iodide here. It just looks different in the equation.
So the K will just basically leave that alone the entire time except it just
Yeah, the
shows
K
up?
plus will just show up. Yeah. I did that one yesterday. There we go. End of new material.